Hello students, today's topic is source of electromagnetic waves. Remember, we are doing the basic information about the electromagnetic waves. Yesterday in the previous lecture we studied about the displacement current, how a varying current applied to the capacitor have a time rate of change of the magnetic flux. So outside the capacitor we have a conduction current, and inside the capacitor we have a displacement current. Though that displacement current was epsilon naught times the change in the electric flux, the displacement current does not mean the motion of the charges in the real sense. Now, what is the source of electromagnetic waves? See, Hertz performed an experiment for the production of an electromagnetic waves, but it was confined in a small area, or it was confined in the laboratory only. So we are not going into detail about the origin of electromagnetic waves, or we are not doing the Hertz experiment. We are simply writing the concepts we have learned in the previous chapter. Now this concept, we know that a stationary charge, or the charge moving with constant velocity, cannot produce electromagnetic waves. Now in the concept of electromagnetic waves, in the introductory part, we understood that the time varying electric field produce a time varying magnetic field, and time varying magnetic field produce an electric field, that is an oscillation of an electric and the magnetic field. So if you take a stationary charge, then we know that it will produce an electric field, and if we take a charge in motion, it will produce electric field and magnetic field. That was a Lorentz force, but they do not change with time. They were not the function of the time. So this portion we know. Now according to Maxwell, accelerated charge should produce a EM wave. So according to Maxwell, if the charge are accelerated, then they are able to produce the electromagnetic waves. Now oscillating charge is an example of accelerating motion. So we take a charge which will oscillate about its mean position. Now when the charge oscillates with certain frequency, it produces electric and magnetic field oscillating in the space. So you have to remember this point, that an oscillatory charge will produce the electric and the magnetic field, which itself are oscillating in the space. Means a charge oscillating give rise to a electric field intensity, which is a function of time, and this electric field will give rise to the magnetic field, which in turn will again produce an electric field. If there are no losses, this oscillation of electric and magnetic field continue in the space. Thus oscillating field produce the electromagnetic waves. So this is the point you have to remember, that oscillatory fields produce the electromagnetic waves, in which the electric and the magnetic field are perpendicular to each other. So we are trying to understand the basic concepts only. We are not going into detail, but there are experiments which have proved or from which an electromagnetic waves can be originated. So we are not going into the depth of the concept. We are simply trying to learn the thing that oscillatory field will produce electromagnetic waves, and when the electromagnetic waves are produced, electric and magnetic field are remain perpendicular to each other, and the electromagnetic waves propagate in a direction perpendicular to the electric and magnetic field. It means, if suppose if the electric field is along the x-axis and the magnetic field is along the y-axis, then the direction of the propagation will be along the z-axis. That is, all three are perpendicular to each other. We will see the cross product relation between the electric and the magnetic field, and the resultant of this electric and magnetic field will give rise to the electromagnetic waves, which will be moving or which will propagate in a direction perpendicular to the electric and the magnetic field. So the basic thing is we have to remember is, according to Maxwell, accelerate charge will produce electromagnetic waves. We take an example of oscillatory charge, because oscillatory charge is considered to be an accelerated motion, and when this charge oscillate having certain frequency, then it will produce oscillatory electric field and oscillating magnetic field. These fields are perpendicular to each other and the direction of the propagation is perpendicular to electric and the magnetic field. Now what is the frequency of EM waves? So if the charge is oscillating with certain frequency, then the frequency of EM waves is equal to the frequency of a oscillatory charge. So if the oscillatory charge has a frequency of 50 Hertz, then the electromagnetic waves frequency is also considered to be a 50 Hertz. It is an example. Now energy of oscillating charge is imparted to the electromagnetic waves. Now we know that energy is neither created nor, it can neither be created nor destroyed. So when the electromagnetic waves propagate, it is the transfer of energy from one place to another. Now what is the source of this energy? So energy of oscillatory charge, so the charge which have a energy provided by an external source is imparted to the electromagnetic waves, and this energy is transferred from one place to the another. Hertz was the first person to prove that light is in electromagnetic waves using lower range of the radio waves. So basically, to prove that light is in electromagnetic waves, we require a very high frequency, but Hertz experimentally proved that light is in electromagnetic waves using lower range of radio waves. Though this experiments were confined to the laboratory only, so whatever electromagnetic waves were produced, they used to travel a short distance. Later on, Jagdish Chandra Bose also produced an electromagnetic waves of shorter wavelength, see the wavelength 25 mm to 5 mm, which was confined to laboratory. Now in today's scenario, the communication is done across the world. The electromagnetic waves travel across the world, but at that time it was confined to the laboratory only. So the transmitter as well as receiver both were in the laboratory, and the electromagnetic waves die down if they are if they travels to a larger distance. Later on, a Macroni, again a name of a scientist, Macroni or Marconi, transmitted electromagnetic waves to several miles. So Jagdish Chandra Bose Hertz experiment confined the electromagnetic waves to the laboratory, or they do not travel a long distance. So Macroni transmitted electromagnetic waves to several miles, and an antenna which transmitted this electromagnetic waves were also known as the Macroni antenna at that time. So this is the source of electromagnetic waves. Overall, you have to just remember that electromagnetic waves is produced due to charge oscillating about its main position. This oscillatory charge will give rise to electric and magnetic field, and the direction of the propagation of electromagnetic waves is perpendicular to the electric and the magnetic field. Now let us see what are the different characteristics of electromagnetic waves. So after the production of electromagnetic waves, we will see that what are the characteristics of electromagnetic waves, how they propagate, and what are the characteristics they possess. Now let us see the characteristics of electromagnetic waves. The first characteristic, which we have already discussed, in electromagnetic waves, electric field and magnetic field which are oscillating are perpendicular to each other as well as perpendicular to the direction of the propagation of the wave. So whenever electromagnetic waves are produced, electric magnetic field are perpendicular to the direction of the propagation. Now as an example, Consider that electromagnetic wave is propagating along z-axis. We assume that electric field is along the x-axis and magnetic field is along the y-axis. Now this is mathematically represented by a wave. Now we know the general wave equation in 11th was y is equal to a sine kx minus omega t, that a travelling wave was represented by the general formula y is equal to a sine kx minus omega t. There the direction of the propagation of wave was along the x-axis. Now in the place there the particles were oscillating about their mean position. Here the electric and magnetic field are oscillating. So Ex is equal to E naught sine kz. Here we have a z because we have assumed the wave is propagating along the z-axis minus omega t. And similarly the magnetic field is By is equal to B naught sine kz minus omega t. In vector form, because it is traveling along the x-axis, its x component is present, the remaining yz component is 0, and for magnetic field the j component or y component is present. So this is a vector form. We put a arrow and I and j, where this will indicates the amplitude or the maximum value of the electric and the magnetic field. So E naught and B naught are the amplitudes of electric and the magnetic field. So this is how we show the diagram. The electric field is propagating along, is oscillating along the x-axis. This is your y-axis, so B vector is along y-axis, and this is the direction of the propagation of the electromagnetic waves, that is along the z-axis. So taking an example, this is the mathematical representation and it is the diagram of the propagation of electromagnetic waves. Now for the application or for the numericals, we have to remember the general formula for the electric and the magnetic field. Now it is not necessary that a wave always propagate along the z-axis. If they have given x here, then the direction of the propagation is along the x-axis. So this is the wave is propagating along the z-axis, positive z-axis. If the wave is propagating along the negative z-axis, we may have a plus sign also here. So if the wave is propagating along the negative z-axis, so we can write this equation as omega t minus kz, or sometime we will also have a plus sign. So depending upon the direction of the propagation, this plus minus sign will change. The direction will also change. We have taken this as an example. So these are the two general equations. These are in the vector form. Then we know that this k is named as a wave vector. So in 11th standard we know the concept of the waves. So the k is known as wave vector. So k is equal to 2 pi by lambda, where lambda is a wavelength, omega is a angular frequency. Now wave speed. We know all the electromagnetic waves travel with the speed of light. So c is equal to omega by k. So all these equations are required for solving the numericals. So c have a relation omega upon k. Now omega can be written as 2 pi nu, means the frequency. K is replaced by 2 pi by lambda. 2 pi get cancelled. So the frequency into the wavelength is also c. So we have a two formula where the speed of the light will remain, the speed of the electromagnetic waves is equal to the speed of light, which remains constant. The frequency and the wavelength will keep on changing. So if one increases, the other should decrease. Third characteristic is the magnitude of electric and magnetic field is related with. So we have a relation C is also equal to E naught upon B naught, that is the amplitude of the electric and the magnetic field. We know that electric field and magnetic field are now the function of time. They oscillate, their value keeps on changing. So if you have a ERMS value of electric field intensity, then we should have a BRMS also. So you can write C is equal to ERMS upon BRMS. We know the relation between the maximum electric field and its RMS value. So that is 1 upon the root 2 times. So this is the third characteristic of the electromagnetic waves. Now let us see the fourth characteristic. Sorry, this is the fourth characteristic. This is the fifth. The fourth characteristic is, in the free space, oscillation of electric and magnetic field are self-sustained. Means the electric field intensity which is oscillating give rise to the magnetic field intensity, and the magnetic field intensity will give rise to the electric field intensity. It means electromagnetic wave is self-sustained wave. It self-sustained, no external source is required to keep its propagation. Only an external energy is to be provided for its production, and then that wave will propagate in the space by itself. Electric field will give rise to magnetic field, the magnetic field will give rise to the electric field. So it is self-sustained, no medium is required for its propagation. Also you have to keep this in mind, earlier it was assumed that medium is required, and the different scientists assumed an universal medium which was called as ether at that time. That universal medium ether is required for the propagation of electromagnetic waves. However, the Michelson and Morley discarded the concept of the ether. So these two scientists, Michelson and Morley, performed an experiment and they discarded the concept of the ether as a medium. It means they are self-sustained, free oscillation. They propagate by itself. That is, electric field give rise to magnetic field give rise to electric field. They are transverse in nature and they are non-mechanical waves. Non-mechanical waves itself means they does not require any material medium for its propagation. That is, it can propagate in vacuum also. See, the sixth characteristic of an electromagnetic waves. The speed of electromagnetic wave is 3 into 10 raised to 8 meter per second and is independent of the wavelength. So in the free space or in the vacuum, this EM waves travel with a speed of 3 into 10 raised to 8 meter per second. That is the speed of the light. Then electromagnetic waves experience, or it shows the phenomenon of diffraction, reflection, refraction and polarization. So you have studied all this phenomenon. So electromagnetic waves also show this phenomenon, or it experiences diffraction, refraction and polarization. Then electromagnetic waves transmit energy and momentum when they travel from one place to another. For example, the light coming from the sunlight is an electromagnetic wave. So the energy is transferred from sunlight to us. So at the same time, the momentum is also assumed to be transferred from one place to another. Electromagnetic waves possess energy, that is written energy. They transmit energy means they possess energy. This energy is called as radiation energy. Then the important characteristic is electromagnetic waves exert pressure on the surface they are incident on it. So they will exert a pressure when they are incident on any surface, and that pressure is called as the radiation pressure. So if I take a unit area on which the electromagnetic waves are incident, then we can say this electromagnetic waves, because they possess energy, they transfer the momentum or they exert the pressure. This pressure is called as radiation pressure, which in fact impart linear momentum to the surface. So the momentum imparted to the surface is change in momentum is equal to change in energy upon C. So this is a relation for complete absorption. So if electromagnetic waves falls on any surface, and if this electromagnetic waves are completely absorbed, then delta P is equal to delta U upon C. And if this electromagnetic waves are reflected back for complete reflection, so if they are incident on any surface and they are reflected completely, in this situation delta P is equal to delta U upon 2C. So you have to remember this two formula, the change in momentum, because they will exert a pressure or they will transfer energy or they will impart linear momentum to the surface. So this is the relation between linear momentum and the energy transfer. Then we have the velocity of EM waves in any medium. See, for the free space or for a vacuum, it is C is equal to 1 upon mu naught epsilon naught. So this is, if you substitute the value of mu naught and epsilon naught in this, you will get C is equal to 3 into 10 raised to 8 meter per second. At the same time, many times the MCQ is asked, what is the SI unit of 1 upon epsilon naught mu naught? So SI unit of 1 upon under root mu naught epsilon naught. So if you remember this relation, it is directly meter per second, and the dimensional formula would be L1T minus 1. So if they ask you what is the dimensional formula of 1 upon under root mu naught epsilon naught, instead of substituting the dimensional formula, if you remember this relation directly, you can write the dimensional formula is L1T minus 1. Remember, if there is an under root, if under root is not there, we have a dimensional formula L square T raised to minus 2. So this is many times an MCQ is asked. Now the velocity of EM waves in any medium, because if the medium changes, the permeability and the permittivity of the medium will change. So the speed of electromagnetic wave will change if the medium is changed. So that is the relation. Now we know that permeability of any medium is equal to mu r times mu naught, or mu naught times mu r. That is the relative permeability. That is the relative permeability of medium. And we know dielectric constant multiplied by epsilon naught. That is what we have studied in chapter number 1. The dielectric constant epsilon naught is equal to epsilon. So we substitute these two values in equation number 9. So we substitute this above value in equation number 9. Then we find that we separate this term. In this place, 1 upon epsilon naught mu naught, we have a C. So we substitute this value as C, and we have another relation where the velocity or the speed of electromagnetic wave is equal to C upon under root mu r K. Now this relation is derived to define the reflective index. Reflective index is equal to C by V, that we have studied in optics. So this is the reflective index formula, and from this C upon V can also be written as under root mu r K. So when the wave propagate from one medium to another, the reflective the reflective index changes by this relation. So these are the characteristic of the electromagnetic waves. So there are many more characteristics of this electromagnetic waves. All the formula which are written here in the box are important for the numericals. So we should directly, we are not proving how this formula, or we are not giving the derivation, we accept it without a proof. 12th characteristic, energy density of electromagnetic waves. Now we have defined the energy density for the electric field and the magnetic field, or the energy density of a capacitor and the inductor. See, basically it is an LC oscillator circuit which is responsible for the propagation of the electromagnetic waves. So we will also discuss this production and the propagation of the electromagnetic waves in JEE or NEET lecture. But basically it is a electromagnetic LC oscillation circuit which gives rise to the oscillating electric and the magnetic field. The charge oscillate between C and L. The basic LC oscillation circuit was done in the previous chapter. So The energy density of electromagnetic wave is the energy density of the electric field plus the energy density of the magnetic field. Now the electric density of the electromagnetic wave is half epsilon naught E square, which we have derived in for a capacitor. For an inductor, instead of epsilon naught we have in denominator mu naught, otherwise the field is directly proportional to the square. So it is the sum of the energy density due to electric field and the energy density due to magnetic field. Now in that situation, in the capacitor or inductor, the electric field and magnetic field was constant, or we have assumed the fully charged capacitor, or you can say a fully charged inductor where the magnetic field and electric field was constant. But here the electric field and the magnetic field are oscillating. They changes their value at every instant. So we take a RMS value of E and B in this equation. So in the place of E and B, we write ERMS and BRMS. Now this is one equation in the form of RMS, or RMS have a relation with E naught. So RMS will be equal to E naught divided by root 2. So we can also do that thing. But if we want a relation in the terms of either E or B, then we know C is equal to ERMS upon BRMS. So in the place of this BRMS, I can write ERMS upon C. So in the place of BRMS, we can write ERMS upon C. So this is the term replaced. Then here we have 1 upon mu naught. So in the place of 1 upon mu naught, we can write epsilon naught C square. So that is, in the place of 1 upon mu naught, we have written epsilon naught upon C square. So either the equation can be written in the form of electric field or the magnetic field. So here C square is cancelled. Half epsilon naught E square RMS plus half epsilon naught E square RMS. So this is the important relation for the energy density, that is energy stored or the energy of electromagnetic waves per unit volume. Similarly, instead of eliminating BRMS and mu naught, you can eliminate ERMS and epsilon naught. So in the place of epsilon naught, we will get 1 upon mu naught, and we know the density is directly proportional to the square of the field. So this is the relation between the electric field intensity and the energy density. Then what is the intensity of an electromagnetic wave? This is energy density. Now the intensity. So let us see that the electromagnetic wave is passing through an area and it is traveling with the speed of light. So what is the intensity when this wave passes through this area or a closed surface? So the intensity of electromagnetic wave is defined as radiant energy. So we know that now energy is transferred from one place to another. Now how much energy or what is the intensity of that energy? So the intensity of that electromagnetic wave is defined as radiant energy passing through unit area. So we consider this area. We know that an area is here perpendicular to the direction of the propagation of the wave. So how much energy is being transferred from this closed surface or through this unit area, which is held normal to the direction of the propagation in unit time, is called the intensity of the radiation. That is, the intensity is defined as energy per unit area per unit time, like this. So we will continue with the 13th characteristic, which will deal with the intensity. Now this intensity can be written as rho into C. So directly we have written here the formula for intensity is equal to rho into C, where we have a relation for rho here. C is the speed of light. Though we can derive this formula also, but we are taking it as a granted. Now let us see the last characteristic. So this was all information about the energy density. Now the last characteristic is about the intensity of the electromagnetic waves. Now next characteristic is intensity of electromagnetic waves. Intensity of electromagnetic waves, as we have defined in characteristic number 12, previous characteristic, the intensity is equal to energy per unit time per unit area. So the energy transferred through a area in unit time is called as intensity. Now energy upon time is power. So this power is equal to intensity into A. So the power of EM waves is also written as I into A. Now in previous characteristic or equation 17, we have written I is equal to rho C, that is equation number 17. Now rho is equal to epsilon naught E square RMS. So we substitute this rho value here. So these are the different formulas for the intensity. So in equation 17 we have written I is equal to rho C. Now from this definition we can derive this relation. So I is equal to energy upon area into time. Now if we take this as a length of the closed surface through which the wave is propagating, so this is a closed surface, closed body through which the electromagnetic waves is propagating with the speed of light. Then we multiply and divide this by L. Now area into length is written as volume. So we have delta U upon volume into length upon time. Now this delta U upon volume, that is energy per unit volume, is density, that is rho, and length upon time, that is the speed of the electromagnetic wave. So this is how I is equal to rho C is defined, but we don't need this derivation here. So this is how I is written as rho into C. So intensity is energy per unit time upon area, power is equal to IA, I is equal to rho C, rho is epsilon naught E square RMS. So we substitute all these values. These are the different forms of the intensity of electromagnetic waves. Now we'll come to the last characteristic where E cross B gives the direction of the propagation of the wave. So in this example, we have taken the electromagnetic wave or the electric field along the x-axis, so I cap, and magnetic field was taken along the y-axis, so j cap, I cross j is equal to k cap. So the wave was propagating along the z-axis. So this is the relation which gives the direction of the propagation of the wave. So this is all about we have for the characteristic of an electromagnetic waves. In the next lecture, we will continue with the numericals of electromagnetic waves, where we require this 20 equations related to the electromagnetic waves. Have a nice day.